Remember in the lab, we were doing a Fletcher machine, but we kept it at a constant speed. Block slide down the work desk, okay? But we don't want it accelerating. We want this to go at a nice, constant, slow speed. So now what we need to think about is what happens when that block moving down the workbench accelerates. It's either getting faster or slower due to its friction and its applied force. So we need to take our net forces and determine each of those and apply this to our Fletcher machine scenario. We have a 5 kilogram block being pulled across a bench in a Fletcher machine. We're going to make some assumptions that the Fletcher machine on the bench, it's flat, it's level. The string that's connecting these things has no mass. And again, the pulley is frictionless, has no mass. So those are some assumptions having this Fletcher machine. The hanging mass is 10 kilograms, and the bench has a coefficient of friction between the bench and the block of 0.2. We need to figure out what is the acceleration. Whenever you have these problems, we want to start by drawing our free body diagrams. So let's figure out what forces are going on. Well, here we have a force of gravity, and here we're going to have a normal force equal and opposite in direction. Friction will be this way, opposing the motion. Do we have an applied force? Well, normally our applied force would be here, but we don't have an applied force. But we do have is this block hanging off the end. And I'm going to call this having a force of gravity. I'm going to call this force gravity 2, force gravity 1 over here, just to keep them separate. Now, we do need to eventually talk about what's going on here with the string, with tension in the string. We'll come to that another day, but there is tension in the string. But what we need to realize is that this force is going to be equal to an FA right there. If FA is equal to FF, the block moves at a constant speed. If FF is greater, it'll slow down. If FA is greater, it'll accelerate. That's what we need to solve. So next up, what I would do is I would start to solve the real quick, easy ones that we know. I have a force of gravity, which is our mass times 9.81 to the correct significant digits. That one is 49. This one, it's 10 kilograms. So that's going to be 98.1 newtons. But we'll go to 2 digits here. My normal force will be 49 newtons as well, because that's equal and opposite to my gravity on the block. So those ones should be quick and easy every time. Now I can calculate my force of friction. Remember, my force of friction is equivalent to mu times my Fn. So that will be 49 times 0.2, which rounded off to the right number of significant digits is going to give me a 10 Newton force opposing the motion of the block. So my FA here essentially is 98. Technically, it's not called an FA, but it's a FG, number 2, but that's 98. So now I can find that my F net is 88 newtons that way. That is critical. Now, the one last trick in solving these problems is when we're trying to find our acceleration. So remember that our F net is mass times acceleration. The problem we have here is we have two masses. And because they are hooked together, they are moving together, and we treat them together. So what we have here is we have 88 newtons divided by, and what we'll do is we're going to add the two masses together. So the first one was 5 kilograms, and the second one was 10 kilograms. So that gives us 15 kilograms. So the acceleration will be 88 newtons divided by 15 kilograms. So my acceleration for this problem is going to come out to be 5.87. We'll round that off properly. I'll write that in 5.87. 5.9 meters per second squared in that direction. Once again, I've drawn a free body diagram for a Fletcher machine. And we can see that we have an 8-kilogram block being pulled in the Fletcher machine. So once again, I always like to immediately, when I have a mass and it's a Fletcher machine, I like to figure out what the force of gravity is on that object. So I'm going to quickly figure out that that's 78.5. I took my 8 kilogram, multiplied it by 9.81. And I quickly know that my normal force is 78.5. So I did that really quick. Do that every time. Then I see it's being pulled by a 6-kilogram mass. So that's my second force of gravity. That's this one over here. And it's going to give me an answer of 58.9 newtons. And that is essentially my FA. Okay. We weren't given the coefficient of friction or the force of friction, so we can't figure that out. But what we do see is that we have an acceleration. So we have an acceleration of 2.3 meters per second squared. And we know that our F net is equal to the mass times the acceleration. Don't forget that this is the mass of the two blocks combined, because they are going to be treated as one system. So we'll take the 14 kilograms and multiply that by 2.3 meters per second, and we will figure out that we have an F net of 32.2. Okay. Once I have my F net, we know that our F net is our applied force, which is this 58.9, subtract our frictional force. So using that, we can figure out that our frictional force is our FA, take away our F net. So the F force of friction will be equal to 58.9 newtons, subtract 32.2 newtons, which is our net force. From this, we determine that our force of friction is 26.7 newtons. And if that was all the question asked was find the force of friction, we'd be done. But what we were asked to solve was, what is the coefficient of friction? So remember that the coefficient of friction is the comparison, the ratio of the frictional force to the normal force. So in this example, we have a force of friction of 26.7 newtons, and our normal force we found way back at the start was 78.5 newtons. So from that, we found that the coefficient of friction for this problem is 0.340.